Hi, everyone. Thanks for still being here at 5 p.m. I'm Malo Deniélou. I'm an engineer in the Cloud Dataflow team at Google. I work, my specialty is what we call auto-tuning. So it's like the intelligent adaptation of the Dataflow service to various environmental and other signals that happen during the work execution. And as part of this, I contribute occasionally and consult on the design in Apache Beam. And this is what I'm going to talk about today. So first, what is Apache Beam? So this is the kind of third talk that talks about Apache Beam today. So I hope you caught one of them, but in case you didn't catch one of them, here's a very short introduction. So Apache Beam, this is the kind of tagline. Apache Beam is a unified programming model designed to provide efficient and portable data processing pipelines. So I've highlighted the keywords there. So unified is for batch and streaming. And this is, I'm not going to talk about this in this talk. However, there are two other keywords, which are efficient and portable. And I'm going to talk about the tension between the two. So what is Apache Beam in a one-slide thing? So Apache Beam is three things. Is a programming model, which is like an abstract concept, is a paper. But its documentation is this idea that you can write data processing pipelines by describing them as a DAG and a set of operations, some sources, some sinks, and how to deal with a lot of things that have to do with how to do windowing, triggering, and so on. The second thing in the Apache Beam project is the SDK. So it's this code that will allow you to write those abstract pipelines. And currently we have two SDKs, one in Java, one in Python, so that you can write your pipeline using your preferred language. And the third leg of Apache Beam is the runner. So the runner is a way to take this abstract description of a pipeline that's been produced by the SDK and then execute it on a particular backend. And currently we support 4 backends. Apache Flink, which is the most familiar in this room, I guess. Apache Spark, Apache Apex, and the Cloud Dataflow managed service. There's the 5th one, which is a direct runner, which is a way to execute locally in your environment so that you can just test and debug your pipeline. So how do these 3 things look like in a diagram? Well, essentially you have initially the SDK. So that's how, as a user, you will write your Beam pipeline. Then the SDK produces an abstract representation, which is then fed to the runner. And the runners will be able to execute the code that was your user code that was described in those SDKs on the workers using what we call the fun runners, and there's a fun API. So that allows you to choose your language of choice, like Python, for example, and yet execute your code in a Flink environment, so that you have language independence and runner independence. So the use cases for Beam and where it shines is that it can show it spans the whole spectrum of batch and streaming processing using very simple API and concepts. So you can go and write in Beam from classic batch with fixed windows, streaming with speculative or late data, retraction, or session windows. So I'm not going to go into those details. There are many talks online that talk about the Beam model and how you write your pipelines about it. But it's a very wide use case framework. And there was a talk earlier this morning about the state API that was recently added to the Beam model to also do streaming processing with state. So what I'm going to talk today is about what happens when you actually want to run those things in production. And one aspect about data processing in production is that the environment changes, and your job executions will have different profiles, and your execution engine has, or it's either your execution engine or you that have to care about this, right? So if you're running in production a streaming pipeline, well, it's very likely that you're going to have some varying workload based, let's say, on the time of the day. If your customers are in North America or they are all in Germany, maybe you're going to have a spike at a certain time of day. And if everyone is asleep, then you have very low utilization. And you have the same phenomenon in batch as well. So in batch, usually you execute your pipeline for maximum throughput. And the way you do it is you execute stage by stage, and you wait for one stage to finish to go to the next, to the subsequent stage. And each stage might have completely different setup, a completely different workload associated with it. And so you might have some stages that would be done on one worker, that's fine, but some would require 1,000 workers to actually reach the optimal throughput, or would be more efficient with 1,000 nodes. So how do people deal with it? Well, usually you configure your job, or you configure your cluster. So you configure your Flink cluster carefully, you consider your yarn, you configure your yarn, you configure your job itself, the parameters of your job. But this comes with a curse. And the curse is that how do you choose your settings? So here is just very, very simplified. It's just to convey the idea is that suppose you have a streaming job and you have a workload, and you want to configure it to do the job you want it to do. Well, the configuration here is symbolized by just a bar, so a single number. So you can over-provision your job, saying, well, I care about the latency, for example. My SLO is low, so I need to over-provision my cluster so that I have enough resources in case there's a spike in traffic, right? Or you might say, well, I don't really care that much about latency. I would prefer to save the cost. And it might be like a really significant cost saving, and say, well, I'm going to on purpose under-provision it because this way I save a lot of money, and my cluster is going to catch up during the downtime, right? So maybe there is a peak of just 1 hour during the day, and after that, well, the cluster is just going to keep up, right? And maybe my analytics will be delayed for that 1 hour, but maybe it's not. It's just for a dashboard or something. So, but that's so the main thing is that a lot of effort when you are running those jobs in production is spent writing the algorithm, your processing. But actually, a lot of effort is also spent on finely tuning those parameters so that you get the best efficiency for your job and for your cluster, right? And you have to make those trade-offs, usually based on test data, not on real production data, or you test in production, which is not so great. So the ideal case, and that's where the Beam comes a bit with a vision, is that the ideal case is that it should not be you who configure the job, it should be the system that adapts to your job. And you should just focus on your algorithm and let the system adapt, right? So to illustrate this, so this was illustrated with kind of a streaming model or streaming idea with a simple curve. To illustrate this, principle, I want to talk about an issue that we have in batch, all right? So in batch, usually you split up when you have multiple stages to execute. You take a stage, you split up in a certain parallelism or a certain number of shards, depending how you call them, but you split them up. You split that stage, let's say 1,000 tasks, and then you spread them, you give them to your workers, right? But what you see, and the larger the scale, the more you see that, is that tasks do not finish evenly on the workers. So some might take double the time of some others. And it might be even if all what they are doing is exactly the same, working on exactly the same amount of data, you know, there's always the environment. You are on the shared cluster, you are on the shared cloud, public cloud. There might be things like this, or it might be that your workload is actually data dependent. So you might have some hotkeys, you might have your key distribution or your data distribution. Actually, a byte in one task is not the same work as in the other task. I often give the example of, well, your input is a list of video files to encode. Well, think YouTube, right? And each video file name is the same size, but actually the work to do is depends on the length of the video or the quality or whatever. So you might end up with some tasks that are really, really much longer than others. And in batch, it's especially a problem because you wait for a stage to complete before going to the next stage. So the more you have those stragglers, the bigger the problem. So what are the common mitigation that exist in the industry? Well, one thing that is usually done is, well, you split equally into equal size, right? But that, as I give the example of the YouTube video, encoding does not really prevent all the issues. One common way to work around is you preemptively oversplit. So the smaller your tasks, the more kind of liquid they become, and so if some workers might complete 10 tasks while some other workers complete just 1 or 2, because those were actually the slow ones, and overall you might average it out, right? The issue with that is that there's an overhead per task, right? And there's only so many tasks you can have. You cannot really create 1 million tasks or 10 million tasks or 1 billion tasks or whatever. You can detect slow workers and re-execute. So I know some Hadoop execution mode can do that. They just kill the worker. So if they detect there's a worker is a bit slow, that has a map task or something on a map-reduced job, just kill the worker and hope that if it re-executes somewhere else, it's going to be faster. But that's really like hoping and praying. And the last one is a bit more elaborate, is that you sample the data. So if your execution, the time of execution, the length of work, depends on, let's say, the distribution of your key or your work, you might be able to sample it first and to get to learn what is the distribution of work, and then you adjust your splitting accordingly, right? So you can do that if, let's say, the data you're processing is in database, and you can do this kind of first sampling, but it's a very costly operation, usually sampling and getting to know this, all right? So to give you a quote from a real blog post, like how to tune your Apache Spark job, the most straightforward way to tune the number of partition is experimentation. Look at the number of partition on the parent RDD and then keep multiplying that by 1.5 until performance stops improving, right? So I don't want to throw under the bus Apache Spark, right? That's not the point, because it's the same for every other processing. And if you knew inside Google how we were doing things, we would do doing things basically the same way, all right? But that should not be the way it works. So that leads to the philosophy that one of the pillars of Apache Beam and in the design, and the idea that we want to build the API for big data for the future, right? And there are 3 points in there. So the first point is that no amount of upfront heuristic tuning, whether it's manual or automatic is enough. Because even if you sample your distribution, there are always runtime issues that are going to come and hit unpredictably. So it could be a network congestion or something else. So that's the first thing. So upfront heuristic tuning is not enough. The second thing is that if your system that can dynamically adapt to get out of a bad situation, then it's going to be way more powerful to get rid of those unpredictable situations than doing anything upfront to hope to avoid getting into trouble, right? So those are the, these main ideas that the system of the future is going to be an adaptive system and not going to be a statically initial configuration-based system, right? And the final thing that links this to Beam is that if your pipeline is actually something that is really fine-tuned to your execution environment, then it's not truly portable. If you fine-tune all the parameters of your job to have a number of, to have a certain parallelism, to have certain limits, or like set the RAM in some workers or something, it's never going to be portable, right? So having this adaptive system and designing it so that it works for adaptive systems is the way you can get this portable and efficient and unified programming environment. So that's how we designed the Beam API, right? And here I'm going to give a couple of examples of those APIs and how they work and how they show you how how they give you a high-level API that you do not have to fine-tune, and then they give enough information to the runner for it to run at scale, optimize, and dynamically adapt. So one illustration is the notion of a bundle in Apache Beam. So a bundle is a group of elements of a P collection. So I don't know if you are familiar, but the idea of a P collection is the abstraction for a parallel collection of elements that is distributed, might be bounded, might be unbounded. So a bundle is a group of elements of a P collection that is processed and committed together, okay? And the APIs that are given to you when you write your parallel processing, so here I give the API for the pardo, there are like 5 entry points for you to write, right? So there is the process element, is the third one here. This is a function that you should override to say what your function should do on each element. So it's like the, that's the do fun, right? That's the actual processing. Most of your processing is going to be there. It's per element. But then we give you other entry points. So we have the setup. So the setup matches with the teardown. It's when you initialize your object. So this is where you're meant to, let's say, open a connection to a database or do things that are costly and you should not do per element, right? But we also give you start bundle and finish bundle. So it's not advised to use those, but they reflect this model. So what does it mean? What do the start bundle and finish bundle mean? Well, the thing is that it doesn't mean, you should not think that a start bundle and finish bundle have a precise semantics in the model. They reflect a choice that the runner can make in how to group elements for maximum efficiency. So you can think it's a bit the opposite of a Spark streaming that has a micro batch strategy that you fix and then you hope that this micro batch, the choice you made, is the right one for your job, right? So I'm a bit stretching the analogy, but it's a bit this idea. So the bundle essentially, if you are in a streaming mode for execution, then usually those bundles will be small because you want to optimize for latency. The runner will optimize for latency, right? And you might have a bit of overhead because those small bundles will lead to more frequent commits. But if you have a classic batch runner that is optimized for batch, then maybe the the runner will choose to have larger bundles because this way there is less overhead. You can buffer your reads more and be more efficient, okay? And so if you really intend to do something in the start bundle and finish bundle, you can do things, but you should not assume that there is a fixed size for a bundle. This is a degree of freedom that is given to the runner to make the right choice. And it might be a different choice per stage, for example. So, to give example of how those bundles come about in batch, usually if you are in a traditional engine, you might say as a user, well, I'm reading from this set of files, split it this amount of ways, okay, a fixed number. Or it might be something that is auto-decided by the runner. It might be like, okay, you're reading these pod files from Hadoop or HDFS, and well, you're going to have one task per pod file. In Beam, what we'd like is that you read from a source, and then the runner will decide how many pod files are needed, or how many tasks will be needed. But you're going to say, but well, how does the runner know from a given source? Well, Beam comes with a source API. So Beam will come with the I/O connectors to many places. So you can read from S3 buckets, you can read from files somewhere, you can read from databases or on Google Cloud or somewhere else. There's JDBC connector, you can read from many places. And so Beam asks for this API to report two things, to implement two methods. One is get estimated size, so that the source, when you read from it, it can give to the runner, say, well, I'm X gigabytes. Okay? So actually I have illustration here. So the runner will ask the source, which is implemented in Beam, and the runner is engine dependent, will ask the source, okay, I want to read these logs. Okay, there's a file pattern on Google Cloud Storage. It's going to ask the size. The source is going to say, well, I've implemented this guest estimated size. My amount of log is 50 terabytes. Okay, the runner is going to say, well, he's going to make his own trade-offs for splitting. Maybe it makes sense in that particular moment. It has 50 workers, or it has 1,000 workers. Maybe there are some constraints in bandwidth. Maybe, there are many, many variables that can come into play at that particular moment, right? So the runner can make the right decision and decide, well, I want to split it in chunks of a given size. And the source implements this split into bundles with a particular size. And so the source is going to return a list of source that are then going to provide the tasks for the engine to process. Okay? So this is the initial splitting, right? But we saw that initial splitting is not enough. So here we've provided the way for the runner to decide what's the best way to do initial splitting, right? Set an initial number of tasks. But we saw earlier that having this is not enough. So you want a dynamic way to adapt because you know that you're going to be wrong. So the way we solve this, so this is implemented only in the Cloud Dataflow so far, but all the APIs are there in the Beam level for all other runners to implement. So we solve this problem using dynamic worker balancing. So imagine, okay, so this is a representation of the execution of a job. On the y-axis, you have the workers. So like each of these horizontal bar represents one worker. On the x-axis, you have the time. And essentially, we represent by this block when a worker is busy with one task. Okay? So you can imagine that the second worker here started at the beginning of the job, and then at this point, after just a little bit, it finished that task. So in green is the tasks that have been done, have been completed. However, for example, the first worker seems to take a bit longer to do that task. So we assume the tasks have been split equally, with equal size. But as we saw, equal size doesn't mean equal amount of time to process, right? And this purple bar represents what is the time now. So at this particular point in time, we have one worker that just completed. So now this worker is idle. And the 5 other workers are busy on current tasks, right? So what you can do is you can predict for each of those tasks what will be the completion time of that task, right? And then you can take an average, and let's say this is the average. And what dynamic work rebalancing does is that based on this average, is going to ask those workers, so the worker 1 and the worker 5, to split and to say, well, don't go till the end of your task, just stop earlier and stop as about the average, okay? And what that means is that these new tasks that are taken off existing tasks, split off existing tasks, can be taken over by the other workers. So a little bit later, what you see is that this big task was actually taken by this guy, or this one was taken by this guy, and you stop having some kind of underutilization of the workers, right? But as we saw, any decision you make is not enough, because actually the prediction we made earlier, they were obviously wrong, because they are always wrong. The execution environment is always is a bit predictable, but it's not 100% predictable. So you do it again. So a bit later, we are at this point, and we predict that the average is going to be, the average completion time across all workers is going to be this. So we split again. Okay? So this is dynamic work rebalancing. So how does it work at scale? So there's this thing called Amdahl's law that shows that, you know, if things are low probability at scale, you have much higher probability to encounter them. So the phenomenon of stragglers is something that happens all the time. And the bigger your cluster, the more is going to happen. So this is a classic kind of MapReduce style job, batch job. So there are 2 stages, like map and reduce. And here we have 400 workers, and we disabled dynamic work rebalancing just to demonstrate the stragglers. So it takes about 20 minutes to do the whole job. And you can see that, well, many tasks, we split initially the tasks like 3 tasks per worker. So you see there is a lot of wasted time, right? There are a lot of workers that are idle because there is no work to be done left, okay? They completed their tasks and there are no more tasks available to pick up. So if you enable dynamic work rebalancing, then you get into a situation where you chop off essentially all the stragglers and you can reassign them. And in a way, you can see it on this diagram here, where there's this tiny blank, which are the small moments where we are waiting for those workers to split, and then we pick up the work, okay? And what happens is that all this is savings, right? Is moments where you can start a new job on your cluster, okay? And the second thing why this dynamic worker balancing is important is because it enables autoscaling. Otherwise, there's no point having autoscaling in your batch job. And why is that? Well, suppose that you have an initial allocation of 80 workers for this job, for example. So same idea. The user did not say how many workers they needed. They let the runner decide. And the runner, based on the size of the data, decided, well, it's likely we'll need 80 workers. But actually, there is way more work than we thought. So dynamically, we're going to see that we are making very slow progress. So we need more workers. And so we have multiple rounds of upsizing, so increasing the size of the cluster to reach actually 1,000 VMs here. Okay? And what you can see is that if you started with 80 workers, maybe you split your tasks, I don't know, 300 ways. So you started with 300 tasks initially. But if you start with 300 tasks, having 1,000 workers is useless, right? So the only way you can make it work if you want to upsize to that scale is if you are able to dynamically split the tasks. So that's where dynamic worker balancing allows autoscaling. And if you don't have that, then autoscaling has much more limited use in batch. And so what you see is that not only dynamic worker balancing help with stragglers, so like all the workers complete about the same time. There's like a kind of couple of minutes here at the end, but they allow the autoscaling to happen. So how is it related to Apache Beam? Well, Beam is designed so that this is possible, okay? So it's designed in particular around the idea of simple progress signals that can be easily understood by the runner so that the runner can make the right decision. And so, and this is those two API functions. So every source should implement those two. So one is to say about the fraction that this task has, this source has read so far. So it's the fraction consumed. And there's an equivalent for unbounded sources. So in source, this idea of how much work there is left is actually related to the backlog. So I've talked mostly about batch, but if you want autoscaling in streaming, well, it's one good metric to start autoscaling, upscaling, for example, is do I have backlog in my pipeline, right? So the Beam APIs gives that signal so that the runner can make the right decision and upscale. And then once you have those progress signals, then you need a way to split the tasks, right? And so this is done with those APIs. So when you implement your sources, you should implement those two methods. One is split at fraction. So if the runner says to a given task, I want you to split at 80%, then the task should be able to do it. And give back here the remaining source. So the things that this worker is not going to do. And the second thing is get parallelism remaining. So sometimes some tasks cannot be split. So this is my example about videos from YouTube. Let's say each file has 10 lines that are 10 videos to encode. Well, you can split by line, but you cannot really split inside the file name. It doesn't make sense, right? So, and so in those cases, upscaling doesn't help if you can't split. So we also, the Beam API also has this signal, which is, well, give me how much more time you can split so that the runner can make the right decision again. I'm not talking about those splitting in streaming. This is coming soon in Beam, so it's under implementation now. It's called the splittable DoFun. So if you're interested in that, you can you can join the dev mailing list on Beam and look at the designs for that. So to conclude, if you want to get the highlight of this talk is about Apache Beam and how to handle both efficiency and portability for data processing pipelines. To learn more, there is a couple of blog posts, and of course, please join the Apache Beam community. Thank you.
Yes.
Hi, could you talk a little bit about just there's a lot of work in queryable state in Flink 1.3. So how does that work with rebalancing and auto?
So as far as I know, Flink does not support the rebalancing yet.
Right.
So I don't know how that would work. So splitting state is hard.
Yeah.
But if the state is per key, there's no reason that, well, it depends where you store the state. So I think someone from the Flink community might be better to answer this. But depending how you store the state, it might still be queryable, whatever worker it's working on.
Right.
I don't know if someone from the Flink community can answer better. Or okay, work in progress. Yeah, exactly. I think it makes sense if you do autoscaling in streaming, maybe, where you want to make it available even if you upsize your cluster, that you give a good API for people to query the state, irrespective on which worker it is. Yeah.
So is this auto-scaling implemented in Dataflow?
Mm-hmm. Yes.
So in case of a streaming application, you mentioned about the runner can ask the source what's the size and then do an initial split.
Yeah.
That doesn't really apply in a streaming scenario, right?
No. Yes. So in streaming, so you can think of the split as the number of partition, or it's usually based on the number of workers you have. And then if you listen to signals like backlog, for example, or some other signals, you can decide to upsize and maybe split dynamically those partition.
Okay.
So that's more like that. So there's the initial splitting might be, so in Dataflow, for example, if you start a streaming job, we're always going to start it with 3 workers by default. And then if that's not enough based on backlog, we just upsize.
Okay.
Right? And you need to react, because in streaming you cannot know the stream before you can of course tell Dataflow that you want 20 workers as well, right?
So does Dataflow have a similar concept to queryable state, or what?
Dataflow does not have queryable state. It has the state API, so it's not the same as that Ken mentioned earlier. So that is also in Beam. So if you want to do stateful computation, you have a state per key and window. Beam exposes metrics though, so you can export metrics in your pipeline, so that are queryable, and so that might be a way. But yeah, it's not exactly the same as it doesn't have that feature that Flink has.
So I'm thinking about a sort of, first of all, like, mostly this fits the embarrassingly parallel kind of DAGs, right? So later, I mean, from my stage 1 to stage 2, I'm rewriting the key and generating new keys. Like, these are composite keys and stuff like that, right?
Yeah.
So at a source level, probably I have a view of what my backlog is. But later on, like, let's say after 2 or 3 operators, I'm actually dealing with a different key space. Yep. So if you will, like, my key range is kind of different. Like, universal key range, but it's different, right? So as an operator, like, if I'm coding that operator, So what kind of, I mean, these callbacks, is it always going to give me that key range to what I belong and kind of make a decision? How does it work internally?
So essentially, if you have multiple stages, they are going to read from somewhere, right? It might be an intermediary source rather than the initial source. And the intermediary source can be shuffled, for example.
Right.
And this implements, all these APIs as well. Mm-hmm. So whatever the stage, you have that capability.
So if I'm kind of defining my graph, operator 1, let's say map, operator 2 is, let's say, filter, right?
Yeah.
So this map operator also should expose certain things for the downstream, basically.
Yeah, so usually if you do map and filter,
they are like,
Dataflow is going to optimize it and make it, but essentially, you don't have to do it. Usually it's done automatically by Beam. It's going to insert everything for you. And usually all the IOs that we provide have those implemented properly. And
the other problem is like data locality, right? So though on surface thing might look like, hey, my key range is too overloaded.
Yeah.
Maybe as a coder, I'm tempted to say that, okay, I can split, right? But the other notion of data being local to me is now gone. Now the data has to be shipped to the other node. So how does Beam optimize that?
So Beam tries to not tell you where your data is. So because it should be an implementation detail. And it's the runner to do the right thing for the execution of the pipeline. We are trying really hard in Beam to make sure that those details of the execution are not exposed, because in a way, any decision you're going to make is going to be wrong at some point. Because maybe your key distribution is going to change or something. All right, I've taken too much time. Thanks.